I want to start today with a kind of a thought experiment.
Okay, I'm listening.
It's actually a variation on a famous philosophical problem, Mary's room. But let's twist it for AI.
Right.
So imagine I lock you in a windowless room. You've never seen a dog, not a picture, never heard a bark, nothing.
Total sensory deprivation on the topic of dog.
Exactly. But inside this room, you have a library.
Yeah.
And it has every single book ever written about dogs.
Okay.
Biology textbooks, poems about golden retrievers, vet manuals, everything.
So I have a complete textual understanding. I know the definition of a tail, the concept of a bark, but I have zero sensory experience.
Precisely. You study for 10 years. Then I open the door and a golden retriever walks in. The question is, do you actually know what it is? Do you recognize it instantly?
Or is there some fundamental gap between the text version of reality and the visual version?
Yeah. And that's the ultimate question of knowledge, isn't it? Does understanding require experience?
It is. And for a long time in computer science, the answer was effectively no. Right.
We built AI in these silos. We had text models that lived in that library, and we had image models that lived in an art gallery, and they never, ever spoke to each other.
But that is changing. And I mean, honestly, it has to change.
It does.
We're looking at a lecture today from MIT's How to AI Almost Anything course, and it's all about cross-modal learning. And reading through this, I got the sense that we aren't just trying to build better tools. It feels like we're trying to replicate how a human toddler learns.
That is a very fair assessment. I mean, humans are cross-modal by default.
Right.
You don't just learn what a cup is by hearing the word.
Right.
You hold it, you drop it, you see the milk spill, you hear it shatter.
Your brain is triangulating reality using all those senses.
Exactly.
Yeah.
So this deep dive is about how we get machines to do that, to, transfer knowledge from one sense or modality to another.
Okay, so before we get into the how, I kind of want to push back a little on the why.
Go for it. We always hear about how AI is eating the world. We have endless data, the entire internet, billions of images, trillions of words. Why do we need to get fancy with mixing senses? Can't we just brute force it with more GPUs and more data?
We can, but only in what we call high-resource domains.
Like cat photos.
Like cat photos, sure. If you want to identify a cat, you're fine. The internet is 40% cat photos.
Probably more.
But think about the domains that actually matter for the future, like robotic surgery or specialized manufacturing or diagnosing rare diseases.
Okay, I see where you're going. We don't have billions of captioned videos of a specific robotic arm soldering a microchip.
We barely have any, and that's the low resource problem. We are data rich in memes, but we're data poor in, physical reality. So the mission of cross-modal learning is to figure out if we can use the stuff we have, tons of generic YouTube videos or Wikipedia, to teach an AI to understand the stuff we have very little of.
Like those medical sensor readings?
Exactly.
So it's essentially trying to get a free lunch. You want the model to learn physics from YouTube so it doesn't have to start from scratch when it's controlling a robot.
I wouldn't call it a free lunch, but it is about efficiency. It's about building a generalist intelligence rather than a narrow specialist.
Okay.
And the source material outlines 3 major ways researchers are doing this. The first one is the universal translator approach.
Right. Transfer learning.
Yep.
This part, I have to admit, I had to read it twice.
It's a bit dense.
The lecture talks about this model called the high modality multimodal transformer, or high MMT. And the claim is that you can feed almost anything into one single model.
Right.
But that seems, structurally impossible. A paragraph of text is a line of words. An image is a 2D grid of pixels. A robot sensor is a stream of voltage numbers. They're completely different languages.
They look different to us, but the core insight here, and this is the real technical leap, is that if you abstract it enough,
everything is just a sequence.
Everything is just a sequence.
Okay, walk me through that. I get that a sentence is a sequence. The cat sat, 1, 2, 3. But a picture of a sunset, how is that a sequence?
You have to force it to be one. You take that 2D image and you chop it up into little patches.
Like puzzle pieces.
Exactly like puzzle pieces. Then you just line them up in a row. Now, instead of a grid, you have a sentence of pixel patches. And you do the same thing with audio frequencies or robot arm coordinates. You serialize reality.
Okay, so you force everything into a single file line. But doesn't the model get confused? If I feed it a stream of numbers, How does it know if it's looking at a pixel patch or a stock price?
That's where the one-hot embedding comes in.
The lecturer mentioned that. It sounded like a digital name tag.
It's a bit more profound than just a name tag.
Okay.
In the math of the model, a one-hot embedding is a vector, so a string of zeros with a single one in a specific spot.
Right.
And when you add that vector to the data, it fundamentally shifts how the model processes the sequence. It shifts the attention mechanism.
So it's telling the transformer, expect the grammar of an image here, or expect the grammar of English text here.
That's the core idea. It changes the context. Like if I suddenly switch from speaking English to French, your brain has to shift gears. You listen for different patterns.
Right.
And because the transformer architecture is so good at finding relationships and sequences, it turns out you can train a single model on all of these at once. They mentioned the MIAVite dataset example.
Yeah, this was the medical task. They trained the model on this.
Yeah.
Grab bag of random sources.
YouTube videos, human behavior datasets, robot sensors.
And then they tested it on a medical diagnosis task.
And this is the key finding. The model that had seen the robot sensors in the YouTube videos did better on the medical task than a model trained only on medical data.
See, that's the part that feels so counterintuitive. How does watching a video of a guy playing Frisbee help an AI diagnose a heart condition?
It's about the underlying physics of the world.
How so?
Time series data has a logic to it. There's cause and effect. Events usually happen in bursts. What goes up must come down.
Okay.
The model learns these fundamental rhythms of reality from the YouTube video, and those same rhythms they apply to a heartbeat or a breathing pattern.
So it's learning the metagrammar of how things change over time.
That's a beautiful way to put it. It suggests that intelligence is just. It's way more transferable than we thought.
You don't need a separate brain for every task.
You just need a brain that understands sequences.
Which brings us to the second paradigm. The lecture calls it co-learning. But I was thinking of it as the study buddy system.
It is a study buddy, but a very specific kind. The idea is that you use a helper sense, let's say vision, while you're training the model.
Okay.
But then when you actually deploy the model into the world to take the test, you take vision away.
Why would you ever do that? If you have vision during training, why not just keep it?
Usually because of cost or privacy, or maybe the sensor just isn't available. Think about a self-driving car. You might train it with expensive LiDAR laser scanners that cost thousands of dollars.
But the car you sell to the consumer only has cheap cameras.
Exactly. You want the cheap camera model to remember what the LiDAR saw.
So it's sort of hallucinating the expensive data.
In a way, yes. And the lecture highlights the Parkinson's disease study, which I think is just the perfect example of why this matters.
This one really stuck with me because of the data disparity.
It's extreme.
The researchers had 10 hours of breathing data from patients sleeping.
10 hours.
And from all that, they had to predict a simple binary outcome. Does this person have Parkinson's? Yes or no?
Think about that from the AI's perspective. You have millions of data points of breathing, inhale, exhale, wheeze, pause.
Right.
And at the end of 10 hours, you get one single thumbs up or thumbs down. That is what we call sparse supervision.
It's wildly inefficient. It's like reading War and Peace, and the only feedback you get is someone saying sad.
Exactly. You don't know which sentence made it sad. You don't know which breath indicated the disease. The signal is just drowned out by the noise.
The model just has to guess.
Precisely. So the researchers used this technique called co-learning via translation. They didn't just ask the model to predict Parkinson's.
What did they do?
They said, here's the breathing data. I want you to use this to predict the patient's EEG, their brain waves, at the exact same moment.
But wait, they had the EEG data.
They had it for the training set. So they forced the AI to take the breathing input and translate it into a brainwave output.
And to do that, the AI would have to actually understand the breathing data in extreme detail.
That is the trick. Brain waves are dense. They change every millisecond. To accurately predict a brain wave from a breath, the model has to notice every tiny nuance in the respiration. It can't just space out. It forces the model to learn a rich, detailed representation of the breathing.
It's like the wax-on, wax-off method from Karate Kid. You're doing this repetitive task-predicting brain waves, which seems unrelated to the fight. But then when you switch to the main task diagnosing Parkinson's, you're suddenly a master.
And the beauty is, when a new patient walks into the clinic, you don't need to hook them up to an EEG machine.
Which is uncomfortable and expensive.
Right. You just put on the breathing belt. The model is now smart enough to find the disease in the breath alone because of that previous training.
That sounds incredibly powerful. But I want to talk about the other side of co-learning, alignment.
Zero-shot learning.
Right. The lecture used the cat example.
Yeah.
This felt a bit like a magic trick to me, so I want to break it down.
It feels like magic, but it's actually about geometry.
High-dimensional geometry. You have to do better than that.
Okay. So the model has two distinct spaces. It has a visual space where it maps images and a language space where it maps words.
Okay.
In the language space, the model knows that the word cat is mathematically very close to the word dog or tail and very, very far from the word truck.
That's standard NLP. Words are vectors.
Right. Now, even if the model has never seen a cat image, it has been trained to align the visual space with the language space.
Meaning?
It knows that, in general, images with tails usually map to words near animal.
So it sees the grainy shape, realizes it has legs and a tail, and it maps that to a point in the visual space.
And then it looks at the language space overlay and asks, what word lives at these coordinates?
And even though it's never seen a cat picture, the spot where the image lands aligns perfectly with the spot where the word cat lives.
It's navigating by map coordinates rather than by memory.
That's a great analogy.
Yeah.
It's checking the GPS coordinates of the concept.
Exactly.
So far, this all sounds like a superpower. You mix senses, you get smarter. You align text and images, you get magic.
It sounds great.
But I was glad the lecture included part 3, because it turns out adding more senses isn't always better.
No.
Sometimes it makes the AI stupider.
Absolutely. More data does not equal more intelligence. We have to talk about video BERT.
This was a Google project, right?
Okay.
They took BERT, the gold standard for language models, and decided to train it on video, too.
The logic seems sound. Humans learn language by seeing things. If I show you a video of a dog while saying dog, you learn faster.
That was the hypothesis. But when they tested it on pure text, tasks like understanding the grammar of a sentence.
Semantic role labeling.
Right, that. The performance actually tanked.
It did. It dropped from around 76% accuracy down to 65%.
That is a massive drop. That's the difference between a usable product and, well, garbage. Why did watching videos break its ability to read?
Think about information density.
Okay.
Language is highly compressed. The word run contains a huge amount of meaning in 3 letters.
Right.
A video of someone running is megabytes of data pixels, lighting, background noise, the color of their shirt.
So the video is mostly noise.
For the purpose of understanding grammar, yes,
Yeah.
It's a distraction. The model spent so much of its capacity just trying to process the visual pixels that it lost track of the linguistic subtleties.
It had cognitive overload.
That's a good way to put it.
There was that one specific example I laughed at, the common sense question answering.
The steel wool example.
Yes. The question was, how do you remove gloss from furniture? And the answer is rub it with steel wool.
Right.
Now, my intuition says seeing a video of that would help. You see the texture of the wool, the scratching action.
But the study found that adding video barely helped at all. It barely moved the needle.
Why?
You have to ask why. And it turns out the text rub with steel wool already contains almost all the necessary information. The visual of someone doing it implies a texture, sure, but does it change the logic of the answer? Not really.
So the lesson here is redundancy.
Redundancy is key. If the visual modality tells you something the text doesn't, like the specific shade of green of a leaf, it adds value.
But if it just repeats the concept leaf in a heavy pixelated format, it's just noise.
You got it.
Okay, so we got transfer learning, the generalistic co-learning, the invisible tutor. The final piece of the puzzle is for when we don't even have access to the model's brain.
When we're dealing with black boxes.
Which is the era of the API, right?
Yeah.
You use GPT-4, you use Claude, you can't look at their weights, you can't fine-tune their neurons directly.
Nope. So how do you do cross-modal learning? You use model induction.
I thought of this as the buddy system, or maybe peer review.
It's essentially models teaching models. The lecture gave a great example about activity recognition.
Trying to spot what people are doing in videos.
Right, like playing golf.
Walk us through the golf setup, because this felt like a detective story where 2 partners are cracking a case.
Okay, so you have 2 independent models looking at the same video. Model A looks at RGB, the static color frames.
It's great at identifying objects. It sees green grass, plaid pants, a white cap.
But it doesn't see motion. It just sees a slideshow.
Got it.
Right. Model B sees optical flow. It doesn't see color or detail. It just sees movement vectors, the whoosh.
So Model A sees a guy in plaid pants. Model B sees a swinging motion.
Now, imagine you have a pile of unlabeled data. Model A looks through it and finds a really clear image of a guy in plaid holding a club. It says, okay, I am 99% sure this is golf.
And it labels that clip golf and hands it to Model B.
It effectively grades Model B's homework. It says, hey, study this. This is what golf feels like.
Okay.
Exactly. So Model B takes that clip. It looks at the motion pattern, the specific arc of the swing. It learns, aha, this specific whoosh means golf.
Right.
Now, Model B goes back to the pile. It finds a clip where the image is super blurry. Model A has no idea what it is.
But the motion is perfect. The whoosh is undeniable.
So Model B says, I know this one. This is golf. It labeled it and hands it back to Model A.
And Model A looks at it and learns, oh, apparently you can play golf in the rain when it's blurry.
It's a positive feedback loop. They bootstrap each other. The eyes teach the motion sense, and the motion sense teaches the eyes.
And the lecture points out this is happening right now with large language models.
All the time.
We see this with distillation, right? Using a massive model like GPT-4 to generate explanations or labels.
And then using that output to train a smaller, cheaper model.
Exactly.
Yeah.
We are entering a phase where most of the data AI learns from will be generated by other AIs. It's the ultimate scaling of model induction.
So let's zoom out. We started with the idea that AI used to be trapped in separate boxes, text, image, audio. Now, through transfer co-learning and induction, those walls are dissolving. But reading this, I kept coming back to one concept, vocans.
Visual tokens.
Right. The idea that to understand language better, we are teaching text models to predict the image associated with a word. We're forcing them to visualize.
We are giving them an imagination.
That sounds poetic, but I want to end on a slightly unsettling thought.
Oh.
If we are building systems that actively rely on imagining a visual reality to make sense of language, we are essentially architecting hallucination as a feature, not a bug.
That's a fair characterization. We are telling the model, to understand this text, you must conjure up a picture that isn't there. So, if an AI needs to hallucinate a world to understand our words, at what point does that hallucination stop being a simulation and start being its perception of reality?
That is...
Are we teaching it to understand the world, or are we just teaching it to dream a version of the world that makes the math work?
That is a terrifying thought. Because if its understanding is based on a dream, what happens when the dream diverges from our reality?
Yeah.
That might be a topic for a future lecture.
Let's leave it there for today. Something to chew on. Thanks for listening to The Deep Dive.
See you next time.